Good morning, students. So, in the last class, we have seen the basic definition of NFA and DFA and a transition example along with the language accepted. So, now let us see the another type of finite automata, which is very helpful for converting the given regular expression to finite automata. So, that is our NFA, right, with epsilon moves. So as you all know, NFA is a non-deterministic finite automata where it is having 5 tuple Q sigma delta Q naught comma F. So sigma is a finite input alphabet. Right. So here what we do is here along with the sigma, right, if the input is 0, 1 or AB, we are having epsilon as a another input state. Okay, so your NFA with epsilon moves is NFA with 5 tuples where Q is a set of finite states and sigma is the input alphabet along with epsilon, and as usual Q naught is your initial or starting state and your F is final or accepting state, right? Your final or accepting state will be a collection of states. More than one final or accepting states will be there, but it should be a subset of your Q. And delta is a transition function, which is a total function from Q cross sigma union epsilon, which results in 2 per Q. Right. So the set of all states P is such that there is a transition labeled A from Q to P, where A is in sigma union epsilon, sometimes referred as an NFA epsilon, other times simply as an NFA. So my dear students, be clear that the base language is the regular language and the expression is a regular expression. To convert the given regular expression to automata, it is necessary for us to use NFA. And when you construct the automata using NFA, it is must for us to have epsilon transitions. So this is your NFA with epsilon moves. So it is same as your NFA, but the only thing is in your input symbol, we'll be using epsilon. And we'll be seeing the conversion of regular expression to epsilon NFA using Thomson construction algorithm later. So let us first see the basic definitions. Right. Now, having seen the formal definition of NFA with epsilon moves, let us see the informal definition. Okay, so your M is an NFA with epsilon, right, where it is a 5 tuple Q sigma delta Q naught comma F, right. So let it be an NFA epsilon. Now, a string W in sigma star is accepted by the machine M, finite automata M, if and only if there exists a path in M from Q0 to a state in F labeled by W and 0 or more epsilon transitions. The language accepted by M is a set of all strings from sigma star that are accepted by M. Right, this is the informal definition of epsilon NFA. You can even pronounce as NFA epsilon or epsilon NFA. Let us see how to solve the problem if you have epsilon as one of the input symbol in our NFA. Now first is you are supposed to find the epsilon closure. Let me see the algorithm of epsilon closure. So the algorithm of epsilon closure is the epsilon closure for a given state is include the state, and from that state if you find a transition for epsilon, you are supposed to include the resultant state. So, define epsilon closure Q to denote the set of all states reachable from Q by 0 or more epsilon transitions. For example, epsilon, so you can see the diagram. Now, what is epsilon closure of 0? What does the algorithm say? First, include the state itself. What is the state? Q naught. So, I will be having Q naught. Then from Q naught, right, for the input epsilon transition, it is going to Q1. So I include Q0, that is the current state, and the epsilon transition Q1. And once again, there is an epsilon transition to Q2. So the epsilon closure of Q0 is Q0, Q1, Q2. Now let us go for the second node, epsilon closure of Q1. So first write the state itself, Q1. Then from Q1, find whether any epsilon transition is there. Yes. So it is Q2. So I have written Q1 comma Q2. Now next epsilon closure of Q2. Right. Now as per the algorithm, first to include the state itself, that is Q2. And you don't find any transition for the input epsilon. Right. So epsilon closure of Q3. Now once again, if you find for Q3, now there is no transition for epsilon. So as per the algorithm, include the state itself, it is Q3. Right. So what is epsilon closure of Q can be said as, it can be extended to set of states by defining epsilon closure of P is equal to, right, union of all epsilon closure of Q where Q belongs to that P. For example, right, so suppose if you want to find the epsilon closure of two states, Q1, Q2. So Q1 is what? Q1, Q2. For Q2, what is the resultant state? Q2. So union of Q1, Q2 and Q2 is Q1, Q2. Now, what is the epsilon closure of Q0 comma Q3? It is Q0, Q1, Q2, union Q3. That is epsilon closure of Q0 and epsilon closure of Q3. Right? So, it is union of Q0, Q1, Q2 and Q3. Okay, students, this is very, very important concept in your Thomson construction algorithm for converting the given regular expression to epsilon NFA. You are supposed to find the epsilon closure, right? After that only we will be able to find the DFA. So if you have NFA, you are supposed to convert that into DFA, right? So from regular expression, so regular expression you are supposed to convert to epsilon NFA, and from epsilon NFA you are supposed to convert to DFA. Yes. Now let us go to the definition of NFA epsilon machines. Right, similar to your NFA and DFA, where you have the string accepted and the language accepted and equivalent definition. Here also for epsilon NFA, we have the basic definitions. Let us assume the automata M, which is a 5 tuple. Let it be an epsilon NFA. Let W be the string in that sigma star. Then the string W is accepted by that automata if and only if, right, here delta cap is your extended transition function. Q0 comma W, at least it contains one final state, right? So we can also say as, let M is equal to 5 tuple, let it be an epsilon NFA. Then the language accepted by M is a set where L of M is equal to W, W is in sigma star, and delta cap of Q0 comma W contains at least one state in F. Another equivalent definition for the language accepted is L of M is equal to W, W is in sigma star, and W is accepted by that machine M, which is the finite automata with epsilon mu. Now let us see the equivalence of NFAs and NFA epsilons. Right. So similar to the equivalence of NFA and DFA, here also we have the equivalence of NFAs and NFA with epsilon. So do NFAs and NFA epsilon machine accept the same class of language? Is there a language here that is accepted by NFA but not by any NFA epsilon? Is there a language here that is accepted by NFA epsilon but not by any DFA? Right. So the observation what was made was every NFA is an epsilon NFA. Therefore, if L is a regular language, then there exists an epsilon NFA M such that L is equal to L of M. It follows that NFA epsilon machines accept all regular languages. But do NFA epsilon machines accept more? Okay. So we have seen in today's session about epsilon NFA, about the epsilon closure algorithm and the equivalence of NFAs and epsilon NFAs. Okay, students. So in the previous session, we have seen about the basic definition of NFA, DFA and about the transition function. And today we have seen about NFA and epsilon NFA and what is the equivalence between them. Okay, next. Now let us see the rules, the protocols, right? We call in our TOC subject the rules and protocols as lemma 1. Right, let M be an NFA, then there exists an epsilon NFA M dash such that L of M is equal to L of M dash. Every NFA is an epsilon NFA. Hence, if we let M dash is equal to M, then it follows that L of M dash is equal to L of M. The above is just a formal statement of the observation from the previous slide. Right. So in the previous slide, we have found what is the equivalence between NFAs and epsilon NFA. Based on that, we are giving this. Right. Next, we will see lemma 2. That is a protocol 2. Let M be an epsilon NFA, then there exists an NFA M dash such that L of M is equal to L of M dash. Let us see the proof now. Now, we all know that M is a finite automata with 5 tuple, and let us define another NFA M dash, right, as this, where final state is F union Q if epsilon closure of Q contains at least one state from F. Right, otherwise your F dash is equal to F. So what will happen to your transition? Delta dash of Q comma A is equal to delta cap of Q comma A. So students listen, delta cap is the extended transition function in epsilon NFA. right? Your delta dash of q comma a we are having for the normal transition, right? So let us see the notes. Now your delta cap is q cross epsilon is result in 2 per q, right? Your m dash has the same states in the same alphabet, the same start state as m dash has no epsilon transitions, right? Let us see the final theorem, right? Let L be a language. Then there exists an NFA M such that L is equal to L of M if and only if there exists an epsilon NFA M dash such that L is equal to L of M dash. Proof. Suppose there exists an epsilon NFA M dash such that the language is equal to language of that M dash. Then by lemma 2 there exists an NFA M such that L is equal to L of M. Only if suppose there exists an NFA such that L is equal to L of M, then by the protocol lemma 1, right, there exists an NFA epsilon M dash such that L is equal to L of M dash. So what is the corollary? The NFA epsilon machines define the regular language. Okay, so you all know that regular language comes under our finite automata. That is, all regular languages can be designed by the finite automata. So which is basically of two types, NFA, DFA. Now NFA with epsilon transition, we call it as epsilon NFA. Okay, students. So we'll be seeing the problem of converting regular expression to epsilon NFA using Thomson construction method in the next class. Thank you, students.